prospects for progress toward more predictive models. This is subtitled Painting by the Numbers because one of the things that we do in creating these models is sort of paint on the electrons which produce the emission that we observe. Okay, so the models that I'm going to talk about, and these are not the only models, are GRMHD based models. These use a procedure which is described in a nice paper by George Wong a few years ago. So we run a fluid simulation, a general relativistic magnetohydrodynamics simulation, which produces some combination of accretion onto a rotating black hole, and then some outflow and some Poynting jets along the normal to the plane of the accretion flow. And once that's run, after spending a few $1,000s in supercomputer hours, we then pull the data from the simulation and we look at individual time slices and assign electron energy distributions on each time slice. And that's important because, of course, it's the accelerated electrons that produce the synchrotron emission that we observe. So the sort of current style of doing this, which is hard to justify, involves a parameterized assignment of a thermal electron distribution at each point in space. And for those in the know, this is called the R-high prescription. And this is sometimes described as painting by those who criticize these models. And then once these are assigned, we can do a radiative transfer calculation where we track the phase space density of photons along geodesics back to the observer and estimate what images of the flow would look like. So at the end of the day, we get synthetic images. And we even get synthetic movies. So these models are useful. I see them in the, behind people in the in the displays here. These explain some important aspects of the EHT images, in fact, most aspects. They explain most aspects of EHT observations of polarization in the galactic center and in M87. They don't explain everything, and there's some notable failures of the models. So I think the most interesting failure is that the models that work best are too variable in the millimeter. This is so-called variability crisis. So in the future, these may explain aspects of dynamical images or movies of M87 and Sagittarius A star. So we're expecting an EHT imaging campaign, a movie campaign for M87 this coming spring. And we've made some predictions for what those movies should look like. And these are used to forecast BHEX performance, since the only way we have of estimating what BHEX is going to see on really long baselines is based on these models. Okay, so these models have strengths and weaknesses. As I said, they don't fully explain the variability in the galactic center. And so the question is, how can we build truly predictive models? All right, so there are a lot of limitations of the GRMHD models, and some of these are astrophysical. So as an example of this, we use some kind of standard set of initial conditions where you have a ring of plasma around the black hole. That may or may not be appropriate. One example of a calculation that tries to get around this is work by Sean Ressler, which looks at inflow of plasma from stellar winds in the galactic center as a source for the accretion onto Sagittarius A star. Some of the limitations are numerical. So, for example, we don't know if the simulations are truly converged, although I think We have some evidence that that's not the case, and there are a number of papers out there saying that the simulations don't show any difference over the range in resolution, any changes over the range in resolutions that's accessible to us. And then finally, and the limitations that I'm going to focus on for just a few minutes are the physical limitations. One of these is that the fluid model that we use may not be justified or justifiable. And another has to do with the electron, what's now called electron physics. So understanding what the electron energies are and what the distribution of electrons over momentum is. Is it anisotropic, as Ramesh was describing in the last talk, or is it isotropic? And that in turn determines the synchrotron emission and absorption and so on. All right, so why do we think the fluid model might not be justified? So as many people have mentioned, under the conditions appropriate to BHEX and EHT sources, where the temperature is high, the electrons are relativistic, and the density is low, the plasma is collisionless or Coulomb collisionless, which means that Coulomb scattering is weak. So the mean free path of electron in plasma of this density and this temperature is of order 10 to the 5 times the event horizon radius. And at these temperatures, the Coulomb scattering cross section is of order the Thomson cross section. So you can use that to estimate the mean free path easily. Okay, so this sounds really bad. It doesn't sound like a fluid at all, with particles rushing in every direction and not experiencing any collisions, because it's the collisions, after all, which make a fluid into a fluid. It's the short mean free path limit that best describes an ideal fluid. But we do have a magnetic field present, and that limits the motions of the particles perpendicular to the field. So I have a diagram here of a proton spiraling around a magnetic field line. This is the kind of orbit that all the charged particles are on. And there's a characteristic radius to this, the gyro radius, which is of order 10 to the minus 7 of the event horizon radius in EHT sources. So this is provides an effective mean free path in the direction perpendicular to the field and makes the plasma behave like an honorary fluid in that direction. So that leaves the direction parallel to the magnetic field, and the charged particles can spiral indefinitely in that direction. But there's a possibility of kinetic instabilities, which can excite waves that move along the magnetic field lines and which can scatter the particles. And this in turn may produce a process called fluidization through the wave particle scattering. And this has been studied in many papers going back to at least to work by Matthew Kuntz in 2014. So we have a situation where the fluid approximation may be justified, but it can't be rigorously justified based on Coulomb scattering. One thing that we do know is that kinetic effects, the fact that the particles aren't tied together into a fluid by collisions, may change the dynamics in certain circumstances. And it's known that in current sheets, places where the field undergoes a strong reversal, in current sheets, the dynamics can change significantly. And there's a really nice paper by Ashley Bransgrove and others looking at balding black holes in a fluid simulation and then comparing that to full up particle simulation. Okay. And in that case, the magnetic field comes off the hole more quickly in the full up particle simulation than in the fluid simulation. Okay, so this is really on the frontiers of plasma physics now. And so we don't really know the answer yet. I think there are also these electron physics limitations, and one aspect of this is that the electrons are not in equipartition with the ions as they are in a fluid. The sort of characteristic energy of the electrons seems likely to be much lower than the characteristic energy of the ions. And of course, it's the electrons which produce the emission that we see. So the big question here is what sets the electron energy? So we need that to understand the synchrotron emission, absorption, and Compton scattering. Uh, there's also the possibility, as Ramesh has discussed at some length, of anisotropy of the electrons. So is the effective temperature of the electrons larger along the field than perpendicular to the field? And that can produce observable changes in the model images that we make. And then finally, there's the possibility of a non-thermal tail on the distribution function. So again, this is a tall order. We need to understand, to build first principles models, we need to understand the heating, cooling, and scattering of the electrons off the population of waves that live in these plasmas. Okay, so again, frontiers of plasma physics question. All right, so we don't have to just throw up our hands, however. We have tools that enable us to understand what's going on in the in kinetic theory. And the key tool here is so-called particle and cell simulations, which enable us to directly model these systems in their full glory, their full kinetic glory. These are so-called particle and cell simulations, or PIC simulations, that Ramesh alluded to. And these are a lot like n-body codes or Monte Carlo radiative transport codes. So one selects a subpopulation of charged particles and just integrates their orbits directly, including the effects of the gravitational field and the electromagnetic field. And lots of people have done this. I think the person who really started doing this in the context of black holes was Nishikawa. But this is I think the paper that sort of opened the modern era of PIC simulations around black holes. It's a nice paper by Kyle Parfrey. And you can see here on this plot the currents and the piece of the current that's parallel to the magnetic field, as well as the particle density in a model of a black hole with embedded in an external magnetic field. Okay, so these PIC simulations are quite computationally expensive. So most of them are axisymmetric still, and many use pair plasmas because it's easier to simulate those. There isn't the same contrast in scales, and they have limited resolution. So this gyro radius is typically something like 10 to the minus 2 or 10 to the minus 3 times the horizon radius in these GR-PIC simulations. Okay, so nevertheless, the PIC gives us a tool to probe the key pieces of plasma physics that go into determining the electron distribution function and determining the dynamics of the ions. Okay, so the PIC simulations don't have to be done in the context of a full black hole simulation. People also do sort of microscopic PIC simulations that try and focus in on a small parcel of plasma. And those are useful in, again, understanding the limits of fluid models and understanding where our simulations may be going wrong. So I'm going to wind this up with a forecast here and say that, we have to, at the moment, we have to use the GRMHD models. There's sort of no way around this for forecasting BHEX performance. And it's also true that not all of these GRMHD source models are consistent with observation. So they have proven useful in understanding which classes of models actually are consistent with Event Horizon Telescope data and eventually with BHEX data. There are serious model limitations here from the kinetic physics, but the kinetic simulations, the particle and stellar PIC simulations, give us a tool to understand the kinetic physics. So we don't just have to throw up our hands and say that we can never make predictive models. In space plasmas, where there's a lot of experience. So for example, in modeling the ionosphere of Ganymede or modeling the interface between the solar wind and the Earth's magnetosphere, there have been very successful models built using fluids plus PIC calibrated closure models. And that have an example paper here from Wang et al. In 2018, which is modeling the magnetosphere of Jupiter around Ganymede. So I guess my forecast here is that the future for modeling EHT and BEX sources is some kind of fluids model with some kind of PIC-inspired closure. And as an example of this, I have an image here from a simulation done by one of my students, Vedant Dhruv, which shows a model which includes the effect of anisotropy in the ions. So anisotropy of the momentum distribution in the ions, which is equivalent to a viscosity. And it turns out, actually, in this particular case, for this set of assumptions, that the ideal models and the ideal models with some kind of PIC-inspired closure are very similar in their outcomes. So I'm going to stop there and happy to take questions.
That was great. Very, really clear. I think Alex has a question. I want to ask something first, if I could, which is, do the kinetic effects include shocks of various kinds in the plasma?
Yeah, so collisionless shocks may look different from purely fluid shocks. We know, for example, that at collisionless shocks in the interstellar medium, you lose a significant fraction of the energy into non-thermal particle acceleration. So that may also happen here.
Alex and then Angela.
Yeah, so lovely talk as always. I wanted to ask you, do you think there's some chance that the non-ideal effects that are not captured by GRMHD are so big that we see something completely different from what we expect based on GRMHD? Or, in other words, phrased more positively, could BEX deliver surprises in plasma physics?
So first of all, I missed Roger's snap, crackle, pop talk today, but I think that's an example of a model which envisions a completely different outcome. Uh, so uh, I guess uh, yeah, it's certainly possible that there's a completely different outcome out there, but let me just make a case here for the approximate relevance of the fluid models, which is that they're based on conservation of mass, momentum, and energy. And the PIC models still have to conserve mass, momentum, and energy. So the sort of lowest moments of the distribution of particles, the lowest momentum space moments, which are related to mass, momentum, and energy density, are still kind of constrained to look like the fluid. And you really have to have very strong higher order corrections to that, higher moment corrections to that, in order to get a completely different outcome.
Thank you.
Thank you. And Angela?
Yeah, great talk, Charles. Compared to the other approximations that we were talking about and in your talk, how worried do you think we should be about radiative cooling? And how does this change if you increase the Eddington ratio by factors of a few or up to an order of magnitude for the demographic sources?
Yeah. So that's a great question. I sort of put that under the heading of electron physics, and that's something I didn't have time to talk about. Uh, uh, as you say, at higher Eddington ratios, that's likely to be more important. And we think it's sort of an order unity effect in M87, which is at a significantly higher Eddington ratio than Sagittarius A star. Uh, and the electron cooling can produce not only a reduction in the electron temperature, but also changes in the isotropy of the electron distribution. It can lead to a more fire hose prone
Mm-hmm.
electron distribution, as Vladimir Zhidonkin has a nice paper on this. So I think that's potentially one of the most important effects, especially for M87.